right? So the distortion, if this thing has been locked, element H will the point at element H will want to twist in this direction, yes or no? So this twist over here, like what we have labeled earlier, all right, this is our pi. Okay, this is our pi, right? So if you look at the distribution, okay, so the distribution, I wonder, is it distribution? I wonder what is a good term. So now if this is our shear, okay, this is our shear, and our shear is equal to TR over J, right? And this will be on our we call it our y direction. Okay. So y direction, so if I would draw our transformation, this is our y direction. Okay. So what we realize now is the shear stress relative. So if the radius get bigger, your shear stress get bigger. Okay. So this is our shear stress distribution. I will not call it y. I do apologize. I call it the radius. Okay. Right. So this is the shear stress distribution due to TR over what? Due to torque or shear is equal to TR over J, right? But what will happen now? Okay, what will happen now if I draw the same thing, right? If I were to draw the same thing, right? Same thing. Now, it's not going to be due to torque now. Okay, I'm not going to consider torque. Now, we're going to consider the force Py. Right? We're going to consider Vy now. So what will happen? So now, if it's due to Vy, so I'm going to draw the same diagram. But now, the shear is equal to VQ over IT. Right? You can have a shear force acting on your shaft. Right? Because moment is going to force multiplied by what? Perpendicular distance. This force will induce a moment and also a what? And also a shear force. So what will happen to this distribution? Right? So this is equal, this is again radius, right? This is your rate. No, I won't call radius now. Now this is based on my y. Why I call it based on my y? Because the first moment of area, the Q is equal to A y bar. Okay, so this distribution now is different. Okay, this distribution now goes like this. Now, tau max will occur when y is equal to 0. So, i.e., element k will be equal to your tau max, which is based on VQ over IT. Element h will be equal to what? Your tau will be equal to what? 0. Okay. So now, the thing is this. In reality, right? In reality, in real life, what was going to happen? Okay, so I'm going to, this is critical. So in real life, okay, in actual application, And later on, you'll see this when we do more examples. You'll see this in actual application. TR over J is a lot bigger than VQ over IT. So what does this mean? Okay, what does this mean? Okay, what does this mean? So therefore, and you will see this is a very standard practice. Okay, so you will see that during the design of transmission shaft, right? The shearing stress induced by the shearing force, V, right, is ignored due to its what? Small magnitude. Okay, we usually ignore it. Okay, but the TR over J, which also induce a shear, cannot be ignored because the forces is very what? The forces is very high. Okay, so now if now we're going to analyze the structure now. Okay, now we're going to analyze the structure now. Okay, of the transmission shaft. So if now we're going to focus on element H. Okay, now we're going to focus on element H. Okay, now we're going to focus on element H. So we're going to view element H now. So this is our X and this is our Z. Okay, so if we view at element H, right? So we have compression in the X direction, and then we have negative shear. Okay, we have negative shear. So we know the bending moment. Okay, for this case, we know that the bending moment stress X will be equal to P over A. So it can be a lump formula. It can be Px over A, right, plus by Mz over Izz y, and then plus by My over Iyy z, right? But we know that one of these will be equal to 0. So either one will be equal to 0, right? Why is that? Because like what we see over here, element H is maximum, then you orientate in a different moment over here, element H is equal to what? 0. So the top one, moment about Z, element H is maximum. The bottom one, moment about Y, element H is equal to what? 0. Okay, so that's why I wrote down here, either one, either on. Yeah, Eugene, what's wrong with you? So either one will be equal to 0, right? So the torque, the shear, so the shear that we draw down here based on this orientation, so the shear in the XZ, okay, so it's X plane, intersecting plane is X axis and the direction Z is equal to shear ZX. Okay, so to calculate this, we know that shear XZ is equal to, hold on, all of a sudden I can't write properly. So this will be equal the torque in the x direction multiplied by C divided by J. Okay. So if we were to construct Mohr circle now, okay, so now we're going into Mohr circle. Okay, so this will be my x point, and this will be my z point. So now we go into Mohr circle. So stress X, you know, is compressive. Stress Z is equal to 0. Okay, and we know that shear XZ is equal to shear ZX, and it is equal to negative shear. But whether negative shear, positive shear does not matter on Mohr circle, right? Okay, so we are going to construct Mohr circle. I'm going to take this element. Oi. So we're going to sketch Mohr circle now. Okay, we're going to sketch Mohr circle. So we know if we sketch this out, this will look like this. Okay, so we don't know the value, but we can sketch Mohr circle. So we know that this is our normal stress, right? And then our shearing stress, I'm going to go towards more negative. This is because the positive is not. Okay. Then you have 2 points. Okay, so we know that stress Z line is over there. And then we have a stress. This is our stress Y line, our stress X line, right? And then the shear. So this is our shear. Then from here, point X, right? The element is going to rotate in which direction? The element is going to rotate in so point X. Okay, fix this point. The element based on this shear arrow is going in a clockwise direction. Okay, so this is X, and Z is going based on this arrow on Z is going to anti-clockwise. So this is Z. So this is your Mohr circle. Right? So from here, you can if you use your protractor. So hold on, so we're going to draw Mohr circle. I'm just eyeballing this, okay? Now it won't move. Finally it did. Hey, I think I got my center long. Okay. So now we got our Mohr circle. Okay. So the first thing that we can calculate from here, yeah, we're going to calculate from here, is your. So we have learned this 2 weeks ago, right? So we are going to calculate our stress average. Okay. So the distance from here to here, we are going to call it our stress average. Okay. So stress average, based on a Mohr circle, is equal to stress X plus by stress Z, right? And then the whole thing divided by 2. Okay. So we know that stress Z is equal to 0. So this is equal to stress X over 2. And then we are going to let this equal to stress M divided by 2. Okay. Where stress M